Welcome to this technical engineering series. Today, we are diving deep into power factor improvement techniques. Specifically, we are going to look at the mathematics and methodology behind correctly sizing capacitor banks to optimize your electrical system's efficiency. Presentation agenda. Here is our roadmap for this session. We will start by establishing the theoretical foundations, understanding the power triangle and its components. From there, we will move into the core calculation methods, breaking down the sizing formulas step by step. Finally, we will cover the practical implementation, including how to select commercial units and where to place them for maximum effect. What is power factor? Let's begin with the definition. Simply put, power factor is the ratio of real power, the power doing useful work, to apparent power, which is the total power supplied by the utility. It is dimensionless, represented as the cosine of the angle phi. The closer this number is to 1, the more efficient your system is. The power triangle. To truly understand efficiency, we must visualize it geometrically using the power triangle. Here, the horizontal axis represents real power in kilowatts. The vertical axis is reactive power in kVAr. The hypotenuse is the apparent power in kVA. Our goal in power factor correction is to reduce that angle, phi, effectively flattening the triangle. Defining the components. Let's define those three vectors. First, real power, or P, measured in kilowatts. This is what turns your motor shafts and lights your lamps. Second, reactive power, or Q, measured in kVAr. This is the power required to magnetize inductive loads. It does no work but occupies system capacity. Finally, apparent power, or S, measured in kVA. This is the vector sum of the two, representing the total burden on the supply infrastructure. Consequences of low power factor. Why is low power factor a problem? Primarily, there are two reasons. First, financial penalties. Utilities often charge significant fees if your PF drops below 0.9 or 0.95. Second, system inefficiency. Excess reactive current generates heat losses in your cables and transformers, essentially wasting energy before it even reaches the load. Slide 7. The culprit, inductive loads. What causes this lag? The usual culprits are inductive loads. Industrial induction motors, transformers, and welding machines require a magnetic field to operate. This magnetization current lags behind the voltage, causing the power factor to drop and the angle phi to increase. Capacitor banks. The solution is the installation of shunt capacitor banks. While motors draw, lagging, reactive current, capacitors draw, leading, reactive current. By introducing a capacitor, we inject a current that directly opposes the inductive lag, neutralizing the reactive demand. How it works? Mechanically, this is vector cancellation. By supplying the necessary reactive power locally, right at the panel or the load, we relieve the upstream utility lines of that burden. This shrinks the vertical, Q, component of our triangle, bringing the apparent power line down closer to the real power line, which reduces total current and system losses. The core formula. Now, let's get into the engineering math. To determine the size of the capacitor bank required, we use this formula, Q_C, the required kVAr, equals P, real power, multiplied by the difference between the tangents of the initial and target angles. Step 1. Identify key variables. Step 1 is gathering your data. You need three specific numbers. P, your active load in kilowatts, which remains constant. PF1, your existing, poor power factor. And PF2, your target power factor, usually 0.95 or higher to avoid utility penalties. Step 2. Calculate angles. Because the formula uses tangents, we cannot just plug in the power factor ratio. We must convert that ratio back into an angle. Using the inverse cosine function on your calculator, determine the angle for your current power factor, phi_1, and the angle for your target power factor, phi_2. Step 3. The tangent multiplier. Next, we determine the multiplier. The term phi_1, phi_2 represents the kVAR multiplier. In many engineering handbooks, you will see K-tables that list this multiplier for various starting and ending power factors, allowing you to skip the trigonometry if you are in a hurry. Practical calculation example. Let's run a real-world scenario. We have a facility drawing a 100 kilowatts load. The current power factor is a poor 0.75 lagging. We want to correct this to a target of 0.95 lagging to eliminate utility surcharges. Executing the math. First, we find our angles. Inverse cosine of 0.75 gives us roughly 41.4 degrees. Inverse cosine of 0.95 gives us 18.2 degrees. We take the tangent of both, finding 0.882 and 0.329 respectively. The difference is 0.553. Multiplying our 100 kilowatts load by 0.553, we see we need approximately 55.3 kVAR of correction. Selecting commercial ratings. In the real world, you cannot order a 55.3 kVAR capacitor. Standard manufacturing steps might offer 50 or 60 kVAR units. The rule of thumb is to round up to the next standard size, in this case, 60 kVAR, provided it doesn't push you into a leading power factor, which we will discuss in a moment. Placement strategies. Placement matters. You have two main strategies. Global, correction places large banks at the main substation. This is easy to monitor but leaves internal currents high. Local, or decentralized correction places capacitors right at the motor terminals. This is more efficient as it reduces line losses throughout your entire internal distribution network. Summary of benefits. To summarize the ROI, correct sizing leads to immediate reduction in electricity bills by eliminating demand charges. It also increases your system capacity, freeing up room on your transformer for more loads, and improves voltage regulation across the plant. Safety and risks. A final word of caution. Do not overcorrect. If your capacitor bank is too large, your power factor becomes leading or capacitive, which can cause dangerous overvoltages. Also, be aware of harmonics. If your facility uses variable frequency drives, VFDs, standard capacitors can resonate and fail. In those cases, detuned reactors are required. Q&A. That concludes our technical overview on sizing capacitor banks. Thank you for your attention. If you have specific questions regarding your facility's calculations, feel free to reach out via the contact information on screen.